Hello friends, I hope you all are doing well. In this video, we are going to talk about Hall effect and its how this phenomena is occurring and its some working and concept and some application. So let's begin it. Okay, as you know, the in Hall effect, basically we take a metal or semiconductor um, specimen to observe this experiment. Okay, so let see the figure that suppose a conducting material and that is like in cube. Okay, I am taking here and suppose and it carrying a current I. See, this is your external applied voltage. External applied voltage so that current can flow through the conducting material. Okay, suppose metal. As you can see here, that I am taking that x axis here, y axis this is y axis and this is z axis, and in z axis I am taking as magnetic field given in z axis, so that this phenomena can be carried out. Okay, and see, in the direction of magnetic field, the width is w. Okay, and current is given to the material along x axis, and that current is along the width d, this much. Okay, at this width I am giving current to this conducting body. So what happened in this figure, as you can see, that as current is given x cap, the electrons are moving in minus x cap. Okay, as electrons are moving in minus x cap, and here the magnetic field is applied along z direction, means here, and some magnetic field in backward minus z cap, so that a constant uniform magnetic field can be मतलब वो चारों तरफ जैसे फैला के रहना चाहिए यूनिफॉर्मली, इसलिए वो मैग्नेटिक फील्ड एक जेड डायरेक्शन में और एक माइनस जेड डायरेक्शन में मैंने लिया है. एक्सपेरिमेंटल ऐसे ही लेते हैं, ठीक है. So when that electron is moving in minus x cap direction, due to the magnetic field, it try to divert its path along minus j cap. That means when electron is moving in minus x cap, it try to drift towards a minus j cap, because the magnetic force is try to divert its path. Okay, so let's see the expression of magnetic field here. See here, the magnetic field is as you know that qvv, the q is minus e, and velocity is in minus I cap, and magnetic field in z cap. Okay, so force is obviously EVB, I cross j, z will be minus j cap. So force will be along minus j cap, and the electrons are try to deposit along the lower side of the this cube. Okay, so what happened next? As the electrons are moving in downward direction, the upper side is positive charges will be deposited. As okay, positive charges will be deposited, so that a potential difference will be seen there. Okay, you can see a potential difference which is called VH across this. Okay, as you can see, this is the negative side and this is the positive side. So a electric field will induce due to this potential difference. Okay, that is EH, and that will be in downward. Electric field will be downward direction, as its electric field conventional direction is positive to negative. Okay, but here the electric force will be generated, and that will be upward direction, because here electron is deflecting, as you know from the basic that when electron is moving when electric field is applied and electron is moving, its force will be in the opposite direction of the moving electron. Okay, so here the electric force is upward and magnetic field is downward. Okay, at some instant there will be equilibrium arises. Okay, so at that equilibrium point, let's see what happens. See here, at equilibrium the electric field magnitude will be equal to the magnetic field amplitude, magnitude. That means the electric force on electrons will be equal to the magnetic force on the electron. So as you know that electric force is EH QE, and this is QVB. So if you do equal, then Hall voltage, Hall electric field will be VB. Here V is the drift velocity of the electron. Okay, that here electron is moving. If this velocity is the drift velocity V. Okay, so here you can find out that Hall field. Then as you know, the electric field is V by D, and that Vh is the Hall voltage. Okay, so see the things which I have already described. Here the note is also there, so you can refer that. Okay, let's go to the next page. In the next page I have derived the Hall voltage. So how this Hall voltage arises? That Vh by D equal to Eh, which is equal to Vb from the above. Then if you try to multiply En in the upper and lower side, then the expression will be like this. And then as you know that W and D is the cross sectional area. W and D is the cross sectional area of the plate where the Hall voltage is occurring. Okay, so the thing is NA, V and A is the I is the current which is externally flowing through the conductor. Okay, so that VH will be IB by NEW. W is the width of the plate along the direction of the magnetic field. Keep in mind that magnetic field direction there will be width W. Okay, in the direction of magnetic field the width is W. Okay, then Hall coefficient is the another term will arise, that RH is equal to 1 by NE, and that 1 by NE, if you try to put this NE here, then the expression will be E by JBX. Here electric field is in Y direction and magnetic field in Z direction, and J, that is current density, is along the X direction. So the RH will be E by JBX, or otherwise you can say in the term 1 by NE. Okay, so what is the Hall coefficient? We can define it as the Hall field for unit magnetic field for unit current density is the Hall coefficient. Okay, and let's see the figure again and try to understand this thing. See that if a metal or semiconductor carrying current I is placed in a transverse magnetic field, an electric field is in the direction perpendicular to both the direction of current and magnetic field induced. That means you are taking a metal and magnetic field in Z direction and the current is in X direction, and electric field should be in the direction perpendicular to both current and induced applied magnetic field. Okay, so that then there will be an induced electric field form, that is called as a Hall electric field, and due to this electric field a voltage difference also there, that is Hall voltage. So this phenomenon you can call that Hall effect phenomenon. Okay, all these things we have already seen. So we have to go, what is the application of Hall voltage, Hall voltage or Hall effect, what is the application we have to see. So its application is here, whether the substance is a semiconductor or insulator or metal, we can determine by the using this experiment. How? In finding RH, means Hall coefficient, there is one term is N. See, by determining the carrier concentration N from the RH, we can find out whether the substance is semiconductor or insulator or metal. Okay, this is the one application, and the next application is as you can see here, the we can find out also the metal is substance is semiconductor. So as you know, the semiconductor is of two types, N types or P types. So we can also find the types of semiconductor. Okay, how? That N type, if its RH is negative, and negative if the direction of electric force is opposite to the direction of drifting electron, that is N type. Okay, so you can say it as N type. And if the direction of electric force is same in the direction of drift charge, then this is P type semiconductor. As you can see the figure that here, that electron is drifting downward and the electric force is upward. So this is a N type, but this is a metal I am taking. Okay, if it will be semiconductor, you can say it as N type semiconductor. Okay, similarly, if electric force will be in the same direction of any charge, charge drifting charge, then that will be P type. So let's see the next application. In next application, we can determine the mobility of charge carrier. Mobility, as you know, that if electron is less mass as compared to the holes, then mobility of electron is more as compared to the hole. So as you know, the Vd equal to mu e. Vd is the drifting velocity, equal to mu is the mobility, is the electric field. So you can find, if you know the Vd and induced electric field, you can find out also the mobility. And in another numerical term, you can see that the conductivity is sigma equal to Na mu, and you know the N is the concentration of charge and E is the charge of the electron. And if you know the conductivity of that material, then you can find out also mobility. Okay, and the next application is intensity of magnetic field we measure also. Means the magnetic field which we are taking for our experiment, we can also measure its intensity. Okay, so these are the applications of Hall effect. Okay, I hope you all can understand the concept, and the notes are written by me. You can follow, write it on your notes. Okay, thank you, keep watching.